I wanted to review thermal strategies. And thermal strategies sort of split into several categories. One of those is that the body temperature varies. And the other is that the body temperature is static. Animals where the body temperature varies with the environment are called poikilotherms, and animals where the body temperature is static are called homeotherms. And that just didn't work right, did it? Homeotherms. And that root word homeo is like homeostasis. It means to try to keep an internal constant. Okay, so you've got these two big divisions, and then you've got to decide within this, you can fall into two camps. You can fall into a category which would be an endotherm, and this is where the body generates heat and heat's maintained. Now, your endotherms are really going to fall in this homeotherm camp, where their body temperature should not vary much with the environment. The other category is going to be an ectotherm. And in these guys, the body heat is determined by the environment. In this case, if an ectotherm were to be a homeotherm, this means that its environment must be pretty constant. And in this case, where the body temperature varies, and that's determined by the environment, this animal is going to need to be pretty tolerant of changing conditions. And what I mean by that is if your temperature is going to vary really wildly, you need to be able to survive when it does that. Now, perhaps it shouldn't be surprising that while there's the possibility of an endothermic poikilotherm, these just don't exist. So now I want to take a minute and I want to look at this. I want to look at this tolerance issue. And tolerance can fall into two categories. When we talk about tolerance, you can fall into a category which would be very tolerant, and this would be a eurytherm, or you can be not so tolerant, and this is a stenotherm. Now, maybe these terms seem a little bit familiar because we talked about animals that are tolerant of salinities being euryhaline and not tolerant of different salinities being stenohaline. Okay, so how is tolerance developed. This can fall into two categories: behavioral adaptations or physiological adaptations. Okay, now what are these adaptations? Well, an example for a behavioral adaptation could be curling into a ball. It could be living in a group, like the naked mole rat, where they're kind of cuddling on each other and taking advantage of each other's body heat. It could be living in a burrow. If you're an animal that lives in a hot environment and you're not very tolerant to heat, you might be nocturnal. If you are an animal where your body heat can change with the environment, then you might bask. If you're an animal that lives in a hot environment and isn't super tolerant with heat, you might sweat. Oops. Or wallow. So there are a number of behavioral adaptations that are involved in sort of being tolerant of changing physiologic conditions. And some of them are just avoiding that change. And some of them are coming up with alternative ways to change your body temperature. Now, when we look at the physiologic adaptations, these are really interesting. A lot of these are going to be on sort of the macromolecular level. So we can think of, if we think of enzymes or any kind of protein, right? The physiologic adaptation is going to be changing the number of H bonds. So increasing if you're in an environment where it's hot and you're probably going to lose some, or decreasing if you're in an environment where it's cold and those H bonds would get too rigid and hold your protein together too tight for it to work. For cell membranes, there are a couple adaptations as well. If you are, remember that when we think about a cell membrane, that it's got these phospholipids in it, and those phospholipids are held together by van der Waals forces. And van der Waals forces are really weak interactions, and they're weak interactions that wouldn't really do anything unless there are a lot of them. So basically, there are a lot of little chemical interactions that are going on across this bridge, and that's what's holding these guys together. So when the membrane gets really cold, what ends up happening is, just like in our hydrogen bonds, these bonds get too close together. So what we need to do is we need to make fewer bonds. And one of the ways that we can do that is simple. We just make our little phospholipid tails shorter, and by making them shorter, they have fewer bonds and the membrane is more fluid. Another way that we can do this is that we can take the tail of one of these phospholipid membranes, and we can unsaturate it. When we unsaturate it, we kind of put a little kink in it, and that little kink actually pushes the other guy away a little bit. So it lessens the amount of interaction. Now, we can also change out these phospholipid heads, and we can change them to something that is that's less likely to interact. The last thing we can do is actually add cholesterol. And when we add cholesterol, what's going to happen is now you can think about something kind of getting in between these bonds. It's going to keep them from getting too tight, but cholesterol is kind of funky in that if the membrane's getting too loose, it has something to interact with. So cholesterol actually buffers the membrane. It can be good for both cold temperatures and warm temperatures.